Okay, the title is The Line is Part of a Circle. Okay, I'm going to spend a very small amount of time talking about lines and circles. I just liked this sentence, and it gives the implication of when you're looking at something, it could be you might be looking at part of something bigger, and that bigger thing might have extra structure that makes it helpful to reason about the smaller thing that you were originally interested in. So this happens a lot. So you might have some mathematical object, x, that you are interested in, and it turns out that x is a sub-object of some other object y, where y has structure which is helpful to reason about. And sometimes it can be helpful to reason about x inside y rather than reasoning about it, reasoning about x on its own. Y with helpful structure for reasoning. So an example of that would be the open interval 0, 1 can be embedded inside the circle, which might be described as the closed interval from 0 to 1, and then you mod out by the equivalence relation that simply identifies 0 with 1. So there, the kind of image is you have this open interval, which I'm going to suggestively draw with a bit of a bend, and you find that this can actually stretch and meet up somewhere in the middle at this point, which is not present inside 0 to 1, but it is there inside the circle. And then the circle is a compact space, but the line 0 to 1 is not. And sometimes it's helpful to reason about compact spaces. Another simple example from algebra would be that the real numbers sit inside the complex numbers, where the complex numbers are algebraically closed and the real numbers are not. Okay, so this is a standard concept, a sub-object embedded inside another object with greater structure. And today we're going to be looking at a category theoretic example of this, the so-called Yoneda lemma. Okay, but first I want to talk about embeddings. So let's revisit equivalences of categories. So at one point we mentioned, I think it was inside lecture 3 possibly, that a functor f from C to D is faithful if the function of Homsets which is part of the data of the functor itself, is injective for all pairs xy inside the category C. Moreover, if this map is surjective, then the functor is full. And then, moreover, we had this statement that if for all D inside the category in the codomain of the functor, there exists an object C inside the category in the domain of the functor such that f of C is isomorphic to D, then f is essentially surjective. And there are no points for realizing where that name came from. Okay. Now, at the time, I mentioned that this is a sufficient condition to ensure that F is part of the data of an equivalence of categories, but I never defined what an equivalence of categories was. Back then, I said we need the language of natural transformations in order to be able to write down the definition, and we haven't covered that yet, but we have now. So now I can tell you what an equivalence of categories is. Definition. An equivalence of categories is a pair of functors where f is a functor from C to D, say, and then g would be a functor from D to C, along with a pair of natural isomorphisms between the two composites that can be made of g of f with the respective identities. So, along with a pair of natural isomorphisms, eta from the identity on C to the composition of G after F, and epsilon from F after G to the identity on D. Okay, and so we've got a couple of exercises here. So prove the equivalence between these two notions that I've mentioned. Prove if G is an equivalence of categories if and only if F is full, faithful, and essentially surjective. Okay, and then I can put a hard exercise here. This hard exercise is for those who are interested in foundations, but also just precision. So even if you're only interested in the mathematics behind category theory, you're kind of morally obligated to care about this. Does your proof hold in the first order theory of ZFC set theory? So to give away the ending, it shouldn't. So one direction of your proof should, the other one will require additional assumptions to what are available inside ZFC, but the additional assumptions that are needed are the same ones that are needed in order to even talk about the category of sets, for example, or the category of topological spaces, or the category of groups, all of the categories that we've been talking about so far, category of vector spaces as well. So this was something that I went over carefully inside the Paris version of this course, and I've got the notes written out clearly inside there. So if you need a hint, you can look at that, or we can talk about it inside the exercise session. But there is a small foundations issue, strictly speaking, inside the sentence of the exercise beforehand, that these are completely equivalent notions. Okay. So the reason why I mentioned that is because I want to talk about functors which are full and faithful, but not necessarily essentially surjective. Okay, so the way that we will think about that is an embedding of one category into another. I've realized that I actually have a question myself here. So is that Do we need fullness for an embedding? Is there a difference between a faithful functor? Is that considered as a weaker version of embedding or something?
I don't
I
usually
wonder.
use this term. I wouldn't
Mm.
usually talk about. It's not actually like a very good categorical notion, right? I mean, to be just
So,
surjective onto the set of objects is. Oh, sorry. You mean full? Yeah. Okay. Morphisms. That's
I
full.
don't know.
Yeah. Okay. Yeah.
So,
Uh-huh.
in the reason why I just had the thought was because of the abelian category stuff. So, what is it? The mega theorem. Oh, what's it called?
The mega theorem.
You
The
know what I'm talking about?
the embedding theorem. Is that what you mean?
Uh, yeah, but I'm trying to remember the person's name. So yeah, the
Freed.
embedding theorem,
Freed.
there are two versions of it. Yeah, Freed, that's it, the Freed-Mitchell embedding theorem. So
Mm-hmm.
there's the faithful version of that, which is simple enough, but the full and faithful version of that is super mega. So maybe the category theory community set up a difference between faithful functors and then full and faithful functors or something. I'm not sure.
Yeah.
Anyway,
I think I would. It's not a term that is universally used. So some references might use it, but that doesn't mean that everybody would recognize it. So I would always just say full and faithful functor, I think.
okay, sure. Okay, so I guess the reason why I've put this definition here is to imply to you that for today I'm going to be using full and faithful functors as embeddings. That's how we're going to be thinking about it. And then I can just use this term if I would like. Okay, so I mentioned at the start that we want to look at a categorical situation where we embed a category into another one where that other one has got extra structure, quote unquote. Now, what is that extra structure? In fact, we haven't spoken about universal properties inside this category theory course so far. And I don't have time to go into the full extent of it, which would possibly be to look at limits and co-limits. But instead, we can have a look at an example of a universal property. So I'm going to look at the universal property of a product, and then I'm going to use that to convince you that there is possibility of categorical structure, and that's an instance of it. And then I can tell you some things about the bigger category when we get to the Yoneda embedding, once we've seen an example of what categorical structure looks like. So this is an introduction to universal properties. Okay, in life, it is more important how an object behaves than it is what the object is. For instance, if I was to peg in a tent peg when I'm out camping, I might grab a nearby rock and use it as a hammer. Now, the philosophical question is, does it really matter, or is it even really definable, that what I was using at that point in time was a rock and, strictly speaking, not a hammer? So perhaps you might have the attitude, if it behaves like a hammer, then that thing is a hammer. We can do the same thing mathematically, and this is displayed inside universal properties. So let me give you an example of that. Definition. Let x and y be two sets. A product of x and y consists of a set x cross y and two functions, pi x from x cross y to x and pi y from x cross y to y. And these are required to satisfy the following property. If f from u to x and g from u to y are arbitrary functions with the same domain, then there exists a unique function h from u into the set, which is part of the product, rendering the following diagram commutative. So we have x cross y and our two morphisms, projection onto y and projection onto x. And then we have our two arbitrary functions, f and g. And then we ask for uniqueness of the function h from u to x cross y, which renders this diagram commutative. And what I mean by renders this diagram commutative is that all of the different compositions that you can possibly make inside this diagram are equal when they share the same domain and codomain. So g is equal to pi y of h, and f is equal to pi x of h. Okay, that's a definition. Now let me put some meaning to it. So let's move over to the next set of boards. So an example of a product of sets is given by the Cartesian product of sets. So the Cartesian product, it has the defining property that xy is an element of x cross y if and only if x is an element of x and y is an element of y, along with the two standard projection functions, so x cross y to x, which maps x comma y to x, and similarly for projection onto y. Okay, that's an example of a product. And the proof of it is if I had two arbitrary functions, f from u to x and g from u to y, then what you can do is assume that the necessary h from u to x cross y exists. So I'm going to prove uniqueness first. So assume that this exists. Then for any u inside u, the first component of h of u is given by the projection after h of u, and then similarly for the second component, pi y, h of u. And so this implies that h of u is equal to the pair given by pi x h of u, comma pi y h of u. And then if we have commutativity, then this is just directly equal to f of u, comma g of u. And you can see that this final description of the function does not depend on the function h. So therefore, if it works, then the correct function is the pair f comma g, I don't know why I wrote h there. And we can see that that function does work. So this reasoning simultaneously proves uniqueness as well as existence. Okay, and so the point that I'm trying to make is that this is a familiar object to you. I think that you all know what the Cartesian product of two sets are, but you've probably never seen it defined in this way. And you can notice that we never actually really defined it. I didn't say this is what the Cartesian product is. Well, I didn't do that when I was describing the product, right? So when I define the Cartesian product, you construct a definition. But when I'm defining the product of two sets, of which the Cartesian product is an example, I never actually describe a set and two functions for you. I only describe behavior of them.
Maybe there's a notational thing that's worth clarifying. When you said a product consists of a set, then you wrote x cross y. Now, you don't mean that to denote the usual set of ordered pairs at that point, right? It's just
Right, yeah.
something which you're denoting by that notation that is already familiar to the audience. But and then it turns out by some miracle to be the set that they already know, but it wasn't presumed to be that from the beginning.
Yeah. Yeah, that's a good point. I guess you get used to that if you've done some category theory. So yeah, thanks. Same goes for the projection maps. I had no idea when I wrote down the definition of the product that these were the projection maps from the Cartesian product. You just don't know that. It's just empty notation, and then you find that the Cartesian product with the familiar projection maps are an example of it, which I suppose justifies the notation. Okay, and then, sorry, were you going to say something?
Oh yeah, I was just gonna. There was a comment in the chat from Taskini Alfredo that they would also drop the fullness from the embedding definition. Just FYI.
Yeah. I think that probably makes sense. Okay, so whatever. We're talking about full faithful functors today. Okay, so the definition of the product of two sets, in the way that I wrote it, generalizes to a category theoretic definition immediately. So you literally just replace the word function with morphism and the word set by object, although I guess I need to write exists as well. Okay, let's do it. A product, if it exists, of two objects x and y, in a category C, consists of an object x cross y along with a pair of morphisms pi sub x from x cross y to x, pi sub y from x cross y to y. Which together satisfy the following property. If f from u to x and g from u to y are arbitrary morphisms, then there exists a unique morphism
I think the recording isn't picking up your voice because Dan can't hear you.
Oh, I can hear you now, Will.
Okay, I just moved over a bit. But now I can hear myself twice. Wait, that seems to have stopped now. Okay, maybe it was a momentary glitch. Do you think we're good to
Yeah.
keep going?
Yeah, please keep going. Yeah. Weird.
Okay. So all I was saying was assume that we have another product in our hands. So this is X crossed with a hat, Y, and then row X, row Y. And then we construct the following diagram. We just put the two products together. So I have X cross Y, and I have X cross hat Y, and then I have a bunch of functions. So I've got pi Y, pi X, I've got row X, row Y. And then we just note that this collection of morphisms satisfies the other product's universal property, right? So if I were to look at this could be taken as my U inside the definition of a product, and row Y and row X can be taken as my respectively G and my F. And so therefore, by the universal property of X cross Y, there exists a unique morphism H from X cross hat Y to X cross Y. Just to make sure I don't get confused, I'll actually call that one J, because that's what I wrote it in my notes as. Okay, and then we have the exact same argument reflected over to X cross Y. So we could say this could be taken as G, this could be taken as F, and then this could be taken as U, and then therefore exists a unique morphism, call it H, from X cross Y down to X cross hat Y, which renders the diagram commutative. Okay, and then the observation to make, or the claim, is that these two morphisms compose to give the identity in both respective directions. So,
Sorry, Walter. I think for someone seeing this for the first time, it's such a crucial set of ideas that maybe it's worth writing out the equations that J and H satisfy, just so everybody's
sure.
it's perfectly clear.
So, sure. By the universal property of X cross Y, there exists unique J from X cross hat Y to X cross Y, such that pi X J is equal to rho X, and pi Y J is equal to rho Y, and then by, will be a bit more terse, universal prop of X cross hat Y, there exists unique H from X cross Y to X cross hat Y, such that rho Y, I'll do X first, rho X H equals pi X, and rho Y H equals pi Y. Okay, so that's the important part. And then what you note is, or the claim is, H composed with J makes the following diagram commute. So this is X, X cross Y, Y, and then we can put X cross Y down here as well. So I've got pi X, pi Y, and this is pi X, and this is pi Y, and then I can put H composed with J here. Okay, so the key observation to make is that this is also the same structure of the definition of the product that I've been giving. So I could also look at X cross Y itself as the object U given inside the definition, and then I can take pi Y and pi X to be respectively G and F, and then we have a similar situation. So there exists a unique morphism from X cross Y to X cross Y that renders this diagram commutative, right? But pay attention to the fact that we have the same morphism here and here, and we have the same morphism here and here. So we can think of a morphism that went from x cross y to itself that makes this diagram commutative. The morphism is the identity morphism, right? But then using what I've boxed in green over at the right, we can see that H composed with J also satisfies that condition. Now, the definition of a product is that this is the unique such map. So the identity and Hj are both the unique map that satisfy that property. Therefore, they're equal to each other. So does the identity from x cross y to x cross y. So by uniqueness, the identity of x cross y is equal to H composed with J. Then I'll put in the corner, that's similarly J composed with X is the identity on X cross hat Y. Okay, and that's the end of the proof. Does anybody have any questions? All right. So if a category is such that for every single pair of objects, X and Y, there exists a product, X cross Y, along with the morphisms, then we say that the category admits products, right? And then there are a whole bunch of other types of universal property style definitions that you can describe. You can just have different situations. And these all give examples of categorical structure that your category might have or it might not have. So what we're going to do is look at the Yoneda lemma, which implies a Yoneda embedding, which allows us to embed a category that might not have any of that structure into a category that has actually really quite a lot of structure. So let's have a look at Yoneda. Lemma. So let C be a small category, and all I mean by that is a category whose collection of objects is a set. Somebody's got incredibly loud typing. Thanks. Okay, and let's P be a functor from C into the category of sets. And the statement is for any object A an element of C, there is a natural bijection, let's call it phi, from the set of natural transformations from this functor, hom A comma blank, which maps from C into set. It just takes an element B inside C and returns the object hom A comma B, and then it performs post-composition for the image of morphisms, and then into P. So this is the set of natural transformations from this functor into the functor P. And there's a natural bijection from this into just the set P of A. And the action of this is it sends a natural transformation eta to, well, I can look at eta sub A, and that's now a function from hom A comma A into P of A. So I can just give that the identity morphism on A, and it'll give me back an element of P of A. Okay, and that's a natural bijection. It's pretty cool. So the proof, I'll show you the core idea. So the core idea is the following diagram, and I need to draw this big. So let's jump over to the next set of boards. And it works like this. So given a morphism f from A to X, you construct hom AA to hom AX. And this is hom A, F, so this is the action on morphisms that I was talking about. So it just post-composes with F. And then we can go down to F of A. Wait, F, that's meant to be P. Small typo in the notes there. I'll fix that up. To P of X. And this is just P of F. This is phi sub A. This is phi sub X. Okay, so we can just construct this diagram and look at what the action of elements along these two compositions could be. So let's look at the identity morphism inside hom AA. Now, in one direction, that post composes with F to just give you back F, right? And then if we did have this natural transformation, then phi sub X would be mapping that somewhere. So that would simply just go to phi sub X of F, okay? And then we're going to see if we can, well, we already have the definition of the Yoneda map, and then we're going to see what that would imply for a diagram like this. So if we defined phi sub A of the identity of A going down to our particular element inside P of A, so that's just the image of the Yoneda map that I drew. So I guess I'm saying let U be an element of P of A, be arbitrary. And then this would map along P of F of U. And then to have naturality, we would require an equality there. Okay, so what we're trying to do, let me, now that this is drawn out, summarize and make this make sense. So we're trying to prove that the map that we have is an isomorphism. We also need to prove naturality, but forget about naturality for a second. Let's first prove that we have an isomorphism. An isomorphism in the category of sets is just a bijection, so we need to prove injectivity and surjectivity of this map, right? So first, let's think about surjectivity. So if you give me an arbitrary element U of P of A, then I need there to be a natural transformation that maps onto this element, right? And that's where this part of the diagram has come from. So if I were to go ahead and define that eta sub A of the identity of A maps onto U, then could we extend that out to a natural transformation that maps onto this element U? And this diagram shows you that you can. In fact, it shows you that the definition of the rest, so what we have yet to define is the remainder of the natural transformation. And you can see that it's forced upon us by this diagram. So I need to define phi of X. It's a map from hom AX into PX. And how do I do that? Well, F will have to be mapped to PF of U, which only consists of ingredients that I have, okay? And then if I wanted to prove injectivity, then I need to show that if I had two such natural transformations that are mapping onto the same element U, then those two natural transformations are equal. But again, this diagram shows you that because it shows that this element U completely determines the natural transformation. Because how do I define this? Via PF of U. Okay. So this is a similar style argument to what I showed earlier with the fact that the Cartesian product is a product. So I simultaneously proved injectivity and sorry, what did I show? Yeah, I simultaneously proved existence and and uniqueness by essentially saying if it were to exist, then what would it be forced to look like? And we got a unique answer, and then we looked at that thing and said, does that work? Yes, it does. So if it exists, it must be that. And can it be that? Yes. That's the same thing that's happening here. So if this natural bijection were to exist, then what would it have to look like? And it would have to map the identity from U into PFU. And does such a thing work? Does it give us a natural transformation? Yes, it does. And so therefore we've got injectivity and surjectivity. Okay, so how do I write that out in summary? So surjectivity, every U gives rise to a natural transformation. Eta, such that eta A identity of A is equal to U. And for injectivity, the U uniquely determines this natural transformation. Okay, sorry, kind of snuck that into the corner there. Okay, and the exercise is finish the proof by proving naturality of this bijection. And if you need a hint for that, again, you can look at the notes that I've linked inside the notes to this course. So I did do that in full in the Paris version of the course, and I wrote all the notes out. So try to do this on your own, but if you need a hint, I've written it out fully in the other version of this course. Okay, I'm really sorry. I need to jump away from my keyboard for just 1 second. So just give me 1 minute, please, and I'll be back, and then I'll do a summary. Okay, sorry about that. I'm back. I heard somebody ask a question, but I'm not sure if they got an answer. Did somebody ask something?
Riley asked Dan something, but not there.
Dan's not there. Oh, okay.
Someone told me a local legend about something about Yoneda's lemma that happened to Dan. I was asking if it was true, but didn't know.
Oh, really? Or maybe the silence is him telling you that yes, it's true, and he doesn't want to talk about it. Okay. So yeah, sorry about that, but I'm back. Does anybody have any questions about this proof? Okay. Okay, so that might not immediately look like an embedding, but let me spell it out for you. So I need to mention a couple of things first. We haven't looked at the definition of a contravariant functor yet, so let me quickly get this on the board, and then I'll use it. A contravariant, did I spell that right? Yes, a contravariant functor is an assignment of an object FC an element of D. Well, I should write, say F from C to D. So this is a special type of functor, but that's actually not true, which is the point. So it looks like an adjective. It looks like a contravariant functor is a functor of a certain type, but it's not true. A contravariant functor is a single noun, and it's very similar to a functor, but it's not quite a functor. So an assignment of an object FC an element of D to every C an element of C along with a family of functions. And these are F from hom x y to hom f y f x, okay? And notice the reversal. That's the key point. Satisfying f of g of f is equal to f of f composed with f of g, and f of the identity is equal to the identity. So that's a bit hard and fast, but the point is this is exactly similar to the definition of a functor, but we allow for the interchange of the order of x and y. This is just something that comes up in math a lot, right? So don't forget that if you have the product of two matrices and you take their transpose, or maybe I'll make that the inverse, then you get the inverse multiplied by the inverse. But the order changes, right? Or maybe more generally, if I had two group elements, G1, G2, and I inversed them, then it becomes G2 inverse, G1 inverse. Okay, so there are just sometimes situations where your functor mixes the order of the domain and the codomain, but that's fine. Like a lot of the theory of functors still goes through. It's just that such a thing, strictly speaking, is not a functor, so you need a definition of it. Okay, let me tell you why I'm bothered with such a thing. So there's an exercise here, which is show a contravariant functor is the data of a functor. So let me say a contravariant functor from C to D is the data of a functor from C up into D. Okay, so you can think about contravariant functors as functors if you would like to. It's just you need to be careful with your ops. And the reason why I mention this is because there's also a contravariant version of Yoneda's lemma. So, and then it's the contravariant one that gives you the embedding. So this is going to look similar to what we already looked at. Let C be a small category, and P from C to D a contravariant functor. Then for all A an element of C, there exists an actual bijection from the natural transformations of hom, and now it's blank into A, right? Previously it was A comma blank, that's a functor, and then hom blank comma A, that's a contravariant functor into P and P of A. Okay, and so then what you want to do is look at the special case where P itself is a hom functor. So make that hom blank comma B. Then what we have is a natural bijection between the natural transformations of hom A, hom blank comma A into hom blank comma B, and P of A, where P is hom of blank B. So that's just hom of A comma B, right? And so this is an isomorphism of hom sets. It's a bijection of hom sets. So that's showing you that mapping C, do I have another board? Yes, good. Okay, so what that's showing you, so the point, is the functor which maps C into the category of functors from C up into C. Sorry, C up into set is full and faithful. Okay, because you just need that bijection on the Hom sets, and that's literally what the previous line that I wrote down says. Okay, and then this category of functors is very special. So it admits all products, and that holds true even if C doesn't hold any products, okay? So this introduces products and then a whole load of other universal structure. So I'll write down a bunch of stuff that we haven't defined. There's also co-products. There's also limits and co-limits. There's also exponential objects. And the sub-object classifier. So in fact, what we have is that this functor category is a topos. And what you're meant to take from this board is there's tons of structure here, okay? And then, in fact, even more can be said. So we have this proposition. Every object P inside this functor category is a colimit of objects in the image of Yoneda. Okay, so we haven't defined what a colimit is, but just read this sentence as every object inside this category is some construction applied to objects in the image of the Yoneda. So not only do we embed C into a category with all of this extra structure, we can actually describe all of the extra structure in terms of things inside the image. So this is very, very helpful. A very common thing that we use the Yoneda lemma for is we look at a category C that doesn't have the structure that we need, and then we embed it inside set to the C op, and then use this extra structure, and then see if that reflects down to the original category C. Or better yet, we just concretely work inside this functor category right from the very start. Okay, there's a lot of stuff inside there that I haven't defined, but you can understand the Yoneda lemma with what we've done so far. And my suggestion would be that somebody actually covers this as one of the talks that we're encouraging people to make inside MetaUni for the end of this course. So I'll just write a suggestion. So a really good presentation would be a proof of this proposition. So you'll learn a lot of category theory by doing that. It's a really, really good exercise to do at the start of your journey onto category theory.
Can I just connect some dots here? So if I get this correct, this is your line and circle. That's the
exactly.
So the C is the object you wish to understand better, and then you make it more complicated, but also in some sense simpler by being characterized, by having more properties that you can work with. So maybe if C was R, that's a bit funny, but if curly C was R, then set to the C op would be C. It's a domain in which you can do more things. For example, solve more equations, literally. Finding objects with universal properties is really the same thing as finding solutions to equations. So you can solve more equations. Limits, co-limits exist. And that allows you to maybe solve problems about your original object, in this case C, that yeah, maybe you could have solved in C. It's not like, I mean, any statement you can prove about the real numbers, maybe you can find a proof that doesn't involve the complex numbers if you really try, but that doesn't mean it's the right way to do it.
Mm-hmm. Yep, exactly. Okay, that's me finishing a little bit early, I guess, but that's the end of my that's the end of the planned part of the lecture. Does anybody have any final comments or questions on what we covered today?
Well, it's too good to be true, Billy.
Just the whole story about like throwing in, making it more complicated, and then reflecting results back to C. Just sounds cool, but I think the embedding R into C is a good analogy, because I can think about factorizing polynomials in C is like can definitely reveal more things about R.
Yep. Yeah, one good example would be sheaf cohomology. So you can take a topological space and think about it as a category. So that has as objects open sets, and as morphisms inclusions of open sets. It's a poset, turn it into a category. Then set to the C op is the category of pre-sheaves of sets. And then if you just sort of do algebra, for example, talk about abelian groups in that world, very quickly you'll invent sheaf cohomology, and that is how we define invariance of a topological space often. So there's some sense in which, although if you took a topological space, in some sense the collection of open sets is the whole thing, right? So in any information you want to express about that topological space, whether it's homotopy groups or cohomology groups or whatever, all of that information is in principle there in that set of open sets. But that doesn't mean that it's actually useful to just know the set of open sets, right? That information is not there in a way that you can actually extract and make use of. But in this larger topos, so sets to the C op, somehow you've got the same information, right? In some universal sense, there's no more information in set to the C op than there is in C, but it's somehow there in a way that the structure you're interested in is closer to the surface.
Yeah, that's why I described it as helpful for reasoning, right? So it's not necessarily the case that you unlock anything extra, but it's definitely the case when you actually try to do these arguments that it's helpful for reasoning. Okay, maybe we just leave it there. I was going to say there's only a few weeks left of SOC, so this is lecture 6, and we were planning to do 8 lectures, and then we want to get other people doing talks as well. So just a gentle reminder / push that it would be great to get people doing some talks, and it won't be very, 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 very far in the future that they are going to happen, if they do happen. So please do get in contact with Billy or myself, and let's get some real planning going ahead for these talks.
Yeah, how are they going to be scheduled? So they'll be scheduled in one of these time slots?
Yeah, that's what I was thinking, but
I think that makes sense.
Yeah, I think it depends on how many people talk and stuff like that. But if they're only half an hour, but I think some people want to talk for longer than that. I guess we need the times and then we can work it out. But yeah, I was thinking it was going to... The only problem with this time slot is that we hit Christmas very quickly. So we can do it after Christmas, but there'll probably be a couple-week break or something, and then that's awkward for people to organize talks in that time. Sorry, you go.
Well, just thinking that, I mean, people are often moving to where their family is, or may very soon or already not really be in a place to be preparing a talk. So yeah. it may actually be a good idea to take a break and then rather than get it done in a rush before Christmas. I don't know. I mean, so we have 2 more scheduled weeks of lectures. Is that right?
Yeah.
Yeah.
Yeah. So I've got an idea. So we could do one more lecture for the SOC for now, and I can wrap up the course, so to speak, because the final lecture that I wanted to do was going to be a sample talk to show people what it could look like, kind of thing. And so it was going to be its own standalone seminar, and that was going to be on Moji's notions of computation. So that's a standalone thing anyway. So what we could maybe do is, in January, get SOC going again for a couple of weeks and make it like just the presentations. And the first one is my final lecture, which is just one of the seminar talks, and then everybody else does ones after that. Yeah, so maybe we aim for that. Okay, so in that case, I'll change my statement. It's not necessarily going to happen very quickly. So think about the talks a little bit if you so desire, but I'll just let you all know that you can safely wait until the new year, and then you'll have time to prepare. Okay, so no pressure.
Cool.
Okay. And I guess that means next week will be the final lecture until the following year. And I think that works best for everyone. Okay, we can do that. Sweet. Thank you. Thanks everyone for coming. Let's leave it there.
Thanks, Will.